Thank you so much. So our next speaker needs no introduction. We all know Carver. Carver Mead is known for pioneering the VLSI technology and design methodology that led to the modern electronics era that we have today. But maybe one thing that is less known is Carver's seminal contribution to neuromorphic design and design of neural networks on chip. So today, Carver will share with us some historical views, but I also wanted to talk to you a little bit about this very cool interview that Carver had with Fortune magazine in 1989, which shows how visionary Carver has always been. So the title of this article is Machines Will Understand the World. So this is almost 35 years ago. First, Carver mentions that despite the exponential growth in computing power, computer vision has not been possible yet at that time. But he says that it will happen in this article. He says we are going to see another wave of real artificial intelligence. He's basically predicting what is happening today. And I will read a last section of this interview. There is no question in my mind that we will have machines that understand speech, that understand the world by looking at it. We are going to be able to do that, but it won't be tomorrow. Meanwhile, we'll have small steps. There was nothing wrong with the original vision. We just didn't have the technology to do it. Carver, thank you for joining us today. And I would like to welcome you.
So nice to see everyone. So AI has been big in the news recently. And it's interesting if you look at the trajectory here, the amount of data that was involved in training a neural network was going along with time, and it's going along sort of with Moore's law. So you get more computing, and you can get more memory, and you can train a bigger network. And that was chugging away perfectly well until 2012. Young graduate student Alex Krzyzewski, working in Jeff Hinton's lab up in Canada, and he got fascinated by the graphics accelerators that everybody who was doing fast graphics was using. They were horrible things to program, but if you could ever get them to work, they ran lots and lots and lots of operations. He decided to get one of the big data sets. Fifi Lee here at Caltech had put together a great big data set of images, which everybody owes to her a lot of the training they're doing on pictures and neural networks. So he started training up networks on one of her data sets. He was frustrated because he was working with an old graphics processor from the early 2005-ish sort of data, and couldn't get the whole network into the GPU. It just wasn't big enough, wasn't enough processors, wasn't enough memory. So in 2010, NVIDIA came out with a new graphics processor, and they had two chips that were interconnected. So if you didn't cut them apart, you could work them as a unit. He looked at that and he said, I think I can do that. So he worked like a maniac at the machine level for a couple of years until he was able to do better on the data set than had been done 2 years before in 2010. There's this big contest for people that do neural networks, and they have some thing they want to classify. And the best people in the world at doing computer classification of things, compete to see who can do the best. And he got to where he was doing a little better than the best one from 2010. And so he and his office mate and Jeff Hinton decided they'd go for it. So in 2012, turned out he beat the best other contestant by almost a factor of 2 in the error level. Just walked away with it. It was incredible. Well, that started a wave. And this is what he said about it over here. He said, all of our experiments suggest can do better just by waiting for faster graphics programmers and bigger data sets. So the secret was scale. Scale in memory, scale in number of operations, and scale in the data set that you worked on. And once you got past a certain point, they started looking like they were intelligent. Then you start looking at what happened and the amount of compute people are using to train one up to do one of these interesting things like the GPT things that you're all either working with or hearing about. It's not Moore's law anymore. So over here, Moore's law would be up here somewhere. And what's happened is a factor of 1 million faster than Moore's law over the last decade. So how in the world can that happen? Well, part of it is you can do 1 or 2 orders of magnitude in time just by running it longer, brute force. But you run out of time. It's only been a decade, and you can't train for a whole decade when you want to be on the map today. So it's interesting how we got there, and nobody will tell you the story. So I'll tell you the story today. This is the latest NVIDIA chip, and it's spectacular. And the way in which it's different from earlier ones is these big green areas there are called the tensor cores. And they're arrays of processors that are tightly coupled together. And they're responsible for like 90% of the operations that happen on these machines. So that's the upper right corner of that last plot. Where did the tensor processor come from? Right after they won the big 2012 contest, Hinton and his 2 grad students, Alex and Ilya, had this little partnership, and it immediately got bought by Google. And so Google looked at that for a while and decided that if they were going to field this thing, they were going to run out of data centers. If it got used too much, they'd have to double the number of data centers. Well, that's a no starter. It takes longer than that to double the number of your data centers. So the other thing they could do is make something that would double the capability of the data centers for doing this kind of thing. And so they got onto this notion of very, very parallel digital processing. And so here we are with the tensor processor, and what's the heart of it is this thing, which they said uses systolic execution. Well, what does that mean? Well, what it means is that they have data flowing in the horizontal direction in rows, and they have data flowing in the vertical direction in columns, and at every intersection there's a processor. So it does an operation on the thing that's coming in and sends it out, and it does that every cycle in horizontal and vertical. So it's the most dense thing you can get on a two-dimensional surface, which is what silicon is, 2 plus a few. It was spectacular. It made a big difference. Well, that was a good idea, so then NVIDIA started doing it. And these are the tensor processes you see. But where does that systolic execution come from? There was a young fella at Carnegie Mellon who got onto the VLSI stuff early. CMU was one of the universities we worked closely with during a VLSI age, which started in Caltech in '71 and was getting middle-aged by the time that Kung was at CMU. And one of the things you learn in VLSI right away is that the power and the time come, and the space on the silicon. The majority of it goes into the wires that connect things together and ship data from one place to another. That longer the wire is, the slower it is, and the more wires there are, the longer they have to be because they have to fit in with the others. So what you do is you make things as small as you can and you interconnect them locally and you pass data from one to the other. And HT, who was a good friend of ours in the period, formalized that into this notion of systolic arrays. And if you look at the bottom quotation here, connected to a standard von Neumann computer, a systolic device provides inexpensive but massive computing power. So he not only saw, as all of us did at the time, that you needed to make things local and have them pass data along. We had research projects of that kind going on at Caltech in the mid-'70s. And in fact, Ed Chang is here. Where's Ed? Yeah. Ed is here with us this morning, and you can talk to him about how it was like back in the mid-'70s in the VLSI stuff that was going on here. And he did a thesis on a device which had local processors in it. Every clock cycle passed the data to the next one next to it. So he was one of the first people to actualize a massively parallel computation. And then H.T. Kung made it a more general thing. And H.T. is still going strong. He's at Harvard now. He's had a big hand in coaching people on making systolic arrays work better for neural networks. And I'm glad to see that. Let's talk about energy. Everybody's saying, well, all this stuff is using energy. It's going to heat up the globe. It's going to kill us all. Let's look at what really is going on. And the plot on the right, that's on a log scale, so there are lots of orders of magnitude, 2 orders of magnitude per tick vertically. And the points along that curve are processes by which people are making transistors. Those processes work at a certain voltage, and a minimum transistor has a certain capacitance. So a switching event will dissipate that much energy. And so the minimum computation you could do is to switch one logic element, which would at minimum be one transistor. And so you can then scale all the computing machines in terms of how many equivalent minimum energies they use for a representation of information, say a floating point number. And you can see that the hot CPU back in 2012 on the left plot used just under a millijoule of energy to do a floating point operation. Well, that didn't sound like very much. but it's 10 to the 13 minimum switching units. So somewhere, a lot of information that exists at the bit level is getting involved to do one floating point operation. And you need lots and lots of those to train a network. Well, by the time Alex saw that hot new graphics programming unit, and he got Hinton to buy one for him, they're down by a factor of 3 million from the contemporary hot desktop computer. Well, that's more like it. Now you can see why Alex could do something that people that are doing networks on their hot computers couldn't get close. But it was hard work. And we got another couple of hundred factor by the time we got to the tensor processor with the systolic execution. So this has chugged along. H.T. Kung gave his talk about his systolic system in the 1978 Caltech conference on VLSI. There weren't any other conferences that wanted to hear about it, so we had to make our own conference here at Caltech. And that went on for a few years until it finally filtered out into the rest of engineering and computer science. The other thing you can see from this is the slope of the points, the green and the blue and the red ones, are new processes that are being developed by the semiconductor companies. Well, for us, we were making real chips to do real things. Designing a VLSI circuit doesn't help you if you can't get it fabricated and test it and see what it can really do. I was lucky because I had two former students at Intel, Ted Jenkins, who's now on our board of trustees, and he's here someplace, there he is over there, and Jerry Parker, who is a distinguished alumnus of Caltech, and they were able to take masks that I would get made and run them through the fabs at Intel for the classes we had here and the research projects like Ed's. Ed was at Intel for a while too. We could get fab done because we had friends in the right place. But that didn't help the rest of the universities. So it turns out that what we really needed was a company that would do fabrication for innovative people that were doing innovative designs and making things that worked a lot better. I knew the people in the semiconductor industry, and I talked to essentially all the chief executives at these companies. And they all said the same thing. They said, yeah, we can see that, but we want to own the design. Well, that just killed the program. Because if a small startup company wants to make a very hot product, but just to get it fabricated, they have to give up the rights to it, they're not going to do it. So how are you going to get somebody who will do the fabrication as a business? Well, I kept trying to convince them that doing it as a business would be a good thing. That didn't work very well. Meanwhile, we were thinking about other ways to make highly, massively parallel computing structures. Well, we have an existence proof. The brains of animals do a fantastic amount of computation on very, very low power. And why don't we look at that as a source of organizing principles for computing in ways we never thought of otherwise? And the first student we had that did that was Misha Mahowald, who started out in 1984 to build models of the visual system. Well, the visual system is interesting because the retina is a little outpost of the brain. It's just a very few layer neural system that sits right in front of the photoreceptors and does the processing right there. Well, why would you do that? You got an eyeball, you got to move it. Well, the reason you do that is because you don't want to send the raw intensity of the pixels up to the brain. That'd be way too much stuff and it's almost meaningless. What you want to do is you want to send up the processed information about what's interesting in the image. So in the little circle there, you'll see the circuit that's at the intersection of all these resistors. Well, what are the resistors about? Well, if you have a network of resistors like that, what it does is it takes whatever voltage is at one of the intersections and it spreads it out in space. And because the resistors have capacitance, it also has a temporal delay. Well, guess what? Ernst Mach, way back when, figured out that the two most critical things about the first level of image processing were a spatio-temporal enhancement of the image. Well, how do you do an enhancement? Well, you take the value of the photoreceptor coming in and you subtracted it from the average around it. And that gives you a spatio-temporal enhancement, which tells you that there's something interesting happening at that point in the image. Well, Misha figured that out and built this retina, which she published in 1987. And you can see that's exactly what this circuit does. And by the way, she made the photoreceptor logarithmic. So that meant that the differences that you see in voltage were contrast ratios, which is what you want. You don't want the interpretation of the image to depend on the level of illumination. So the eye goes over 6 orders of magnitude in illumination, still can see. This was the chip that Eric Fossum saw and decided to leave out the processing and call it a CMOS sensor. Misha said something very wise. You do two things when you build a model of what the nervous system is doing. You give neuroscience a synthetic way of checking out if their ideas are really what the nervous system's doing. Because if you can build it and it does what you see the nervous system doing, then you're starting to understand. That's very important for neuroscience. But also, once you've done that, now you have an engineering discipline. And you can start making real engineering systems, which is what Azita and other people looking at today are doing such a wonderful way. We have ultra-parallel digital systems from the 70s that are just now, 50 years later, becoming mainstream and dominating the headlines in not just computer science, but in people's lives even. 50 years. Caltech was at year 1. Then we have vision sensing, hearing sensing, touch sensing, things where we're emulating what the nervous systems of animals do, trying to learn. And of course, that is just really getting started. If you look at the generalization of the silicon retina, what's it doing? Well, it's taking inputs, lower left corner here, and it's making a model, and that's, in that case, the spatio-temporal model of the resistive network. That's a model of an image that's flat and doesn't change with time. That's the model. And then if it doesn't change for a while, it's an image which isn't flat, but hasn't changed recently. So it's a dynamic model of the image, and it extracts interesting things and passes them on up the optic nerve to the rest of the nervous system. Well, you could generalize that. Suppose you made a general system that has an electronic model and it has a comparator. What the model does is to predict the future. It's obviously necessary for any living organism to be able to predict the future, because if you can't, you get eaten by someone that can. So living systems all have to do this. Well, you could do it this way. You make the model, and the model has some parameters, and if you correctly predict the future, you don't send any outputs on up. But if an input predicts an output that's really different, you better pay attention to that. So you send it on up to higher levels of processing. You can make many levels of that, and you can see it could be pretty intelligent once you've made a number of levels that did that. We haven't begun to do that. What we're doing now is this thing. This is what GPT does with text. We haven't scratched the surface of neural computation. That's in the future. And it all starts with what we learn about the real world. Right now, we're using things that have been digitized and put out in the network as our view of the world. That's a tiny, tiny part of the world. And we think it's marvelous it can do anything with that. It's already been turned into machine-readable form, digital form. It's a tiny part of reality. It isn't even part of the same reality. It's a part of bits in memories there, not part of the real world. So there's lots to be done. An idea that came even earlier in the period where H.T. Kung was inventing his systolic arrays, and Marina Chen was a grad student here in the 70s and did a thesis which was way ahead of its time. She saw that what we needed if we're going to do any of these systems was a way to precisely specify what they were. And that specification had two sides to it. One was the behavior of the system, and the other was the implementation. And that implementation could be neurons in a brain, but we hadn't got to that yet. So our implementation was transistors on silicon. And you had to be able to specify rigorously what the transistor network was, what the behavior was. You had to be able to execute it, so she built a whole language on top of this piece of theory that would execute this specification. It was way ahead of its time. I don't think people still have that. Do they, Marina?
New incarnations, many incarnations.
She says there's many incarnations now. I'm glad to hear that, because it was way, way ahead of its time. And Marina went on to be head of computer science at Boston University and had a fantastic career. And we're lucky to have her with us today. Well, while she was doing all that, she was in a group that was getting silicon fabricated at Intel in a way that only worked for Caltech and only worked as long as Ted and Jerry were in position to sneak it through. I did tell Bob Noyce about it when I said, Bob, I want to tell you that I'm sneaking runs through your fab. And he looked at me and he said, Carver, I don't think I want to hear that. So, so you could talk to Ted about how that all worked. But what we really needed was what's now called a silicon foundry. We needed a company that would just fabricate chips according to the designs that the customer had. And the customer would then have the entire ownership of all that. She heard me mumbling and grumbling about not being able to get semiconductor companies to do anything like this. And instead of ignoring me, she actually decided to do something about it. There is now a company that does nothing but fabricate chips for other people's designs. And that's all it does. And by the way, it fabricates not just special purpose chips for people's internal projects, but there are these things now called fabless semiconductor companies like NVIDIA that make a whole product line. That's fabricated by TSMC. The T stands for Taiwan, so that's where Marina got her undergraduate degree. It's now the most successful semiconductor company in the world. And it all started by Marina Chen, and she's going to tell us the story.
Hi, thank you, Carver. It's really a great privilege for me to shed a little light on the lesser known but monumental contributions of Carver to the global economy. Consider the remarkable success of TSMC, now the world's leading chip maker, and the dominance of the Taiwanese semiconductor foundries, commanding about 60% of the global market and 90% of the advanced chips. Is this merely a stroke of luck, or is there some more to the story? Okay, so here we go. Rewind to the early 1980s when Taiwan's Hsinchu Science Park, aspiring to replicate the success of Silicon Valley, was in its infancy. It was here, under the guidance of K.T. Lee, later hailed as the father of Taiwan's economic miracle, that Carver played a pivotal role. Invited by Lee, Carver visited the Industrial Technology Research Institute in Hsinchu at the Science Park, where his visionary ideas about silicon foundries and the spirit of free entrepreneurship were not only embraced, but diligently applied. This encounter set in motion a series of events that would reshape technological landscape. Indeed, what unfolded thereafter is nothing short of historic. And I thank you very much.